Okay, so this is our new chapter, the origin of energy band in solids. So as I have mentioned previously, we have studied why the two atoms come close to each other. That is the bonds in solid. Okay. Now in a solid, when the atoms come close to each other, what happens to their energy level? We're going to study that thing. Here you can see the energy as a function of the interatomic separation. So there's energy in as an interatomic separation. When the interatomic separation is very large, that means there is no interaction between the atoms. So each atom will have their different. Each atom has got different number of electrons, and they have different energy level. Okay. When they are coming close to each other, okay, so that means when they come to the equilibrium separation, the bond exists between these two atoms. Okay, and we have seen that there is a reduction of energy. Okay, so an isolated atom possesses discrete energy of different electrons. Like here, an isolated atom means that interatomic separation is large. Suppose two isolated atoms are, in this case, two isolated atoms are brought two very close to each other. Okay, then the orbit of the two atoms interact with each other, so that the combined system, the energy of the electron will not be the same as the energy level of the individual atom, and the energies will be slightly lower, because when the bond is formed, there is a reduction of energy. So at place of each energy level, a closely spaced energy levels exist. If n number of atoms are brought together to form a solid, and if these electrons interact and give n number of closely spaced energy level. Like when we said two atoms are close to each other, then two different energy levels exist there. But when n number of electrons are brought together to form a solid, then there is an n number of closely spaced energy levels in the place of the discrete energy level, and it is known as the band of allowed energy. That means when the atoms are free atoms, okay, or the interatomic distance is very large, their energy level, these we call energy levels. That means each electron has got different energy levels. When they come close to each other, there is an interaction between them. Okay, and when suppose you have one atom, okay, and suppose consider the sodium atom. So in case of sodium atom, you have energy level 1, and how many electrons are there? 2 electrons are there. And you have energy level 2, how many electrons are there? 8 electrons are there. And then energy level 3, how many electrons are there? 1 electrons are there. Okay. Okay, so when you are bringing two atoms, so their energy level, each energy level will be slightly lower. Okay, slightly lower. When you are bringing n number of electrons, so there is an interaction between the n energy levels. So in when the interatomic separation is less than that of the equilibrium separation, there will be n number of closely spaced energy levels. Okay, so these n number of closely spaced energy levels, actually they will make a bond. Okay, they will make a band, energy band. So that is why we call it energy. That's how the energy bands are formed in solid. So actually the exact to explain the exact to explain the energy band exactly, we need to use the quantum mechanics. Okay, later on we are going to use these quantum mechanics to find out why the energy, how the energy bands are formed. Okay, so there is a model called Kronig Penney model, supports the existence of these energy bands. That means there is an allowed, we'll see there is an allowed band. These are the allowed band, and then there is a forbidden gap, and then allowed band and the forbidden gap. So the mathematical solution of the Schrodinger wave equations, we will use quantum mechanics or wave mechanics to explain the formation of the energy band. Now you see that the conventional way of representing the electron band structure in solid is shown in, we have shown in this figure. The electrical properties of solids are the consequence of its electron band structure. So electron band structure is very important. Okay, that is the arrangement of the outermost electron band and the way in which they are filled with electrons. Okay, and here there are 4 different pictures are there, and as you can see, 4 different types of band structure are possible at 0 Kelvin, at absolute 0 temperature. So in the first figure, the outermost orbit is this one, is outermost band is only partially filled with electrons. The energy corresponding to the highest fill level at 0 Kelvin is called the Fermi energy, is this one. This one is called the, so electrons are filled up to this level. So that level is called the Fermi level. And then there is an empty state, and then there is a gap, and then next allowed band is there. So we'll explain this thing later on. The energy band structure is typified by some metals, in particular those that have single s electron. Okay, and for the second band structure, also find the metals. So in case of metal, there is an overlapping of the this is called valence band, and that is called the conduction band. Why that is called the conduction band? Because when the electron jump from valence band to conduction band, so electron become free. So in case of metal, there is a overlapping of the valence band and conduction band, and Fermi level is here. And there is another one is called, so this is the, when the band gap is very small, we call it semiconducting material. When the band gap is large, then no electron can jump from valence band to conduction band. This is the band structure of semiconducting materials. This is the band structure of metal, and this is the band structure of insulating materials. Okay, so actually there are various models of the there are various model for the the first one is the classical free electron theory of metals. It's a classical free electron theory was introduced by Brillouin in long time ago. It's very old physics, and then later on it was developed by Lorentz in 1909. Okay, and the assumptions of these models are the valence electron of metallic atoms are free to move in space between the ion from one place to another place within the metallic specimen, similar to the gaseous molecule, so that the electrons are called free electron gas. And these electrons also participate in electrical conduction, and hence these are called conduction electrons. And second assumption is there is no interaction between these conduction electrons. And the interaction of free electron with ion core is also negligible. The free electron find uniform electric field of positive ion and that of the electron in the metal. And these free electrons participate in electrical conduction, hence they are called conduction electron as well. The metal possess some physical properties. They are actually due to the existence of large number of free electrons, metal possess high electrical and thermal conductivity. That means their resistivity is low. Their resistivity is low. And also they obey Ohm's law. So you have studied Ohm's law earlier. The current through a metal is actually proportional to the applied electric field. And resistivity is actually proportional to the fifth power of the absolute temperature at low temperature. Okay. So low temperature means that is called below Debye temperature. I don't know. But whereas the resistivity is proportional to the absolute temperature in the high temperature. So there is a temperature called Debye temperature, theta D. Above theta D, it is proportional to T, and however at low temperature it is actually proportional to the fifth power of the 10 to the power 5. Or some theory says it is also proportional to D by 10 to the power 3/2 as well. In metals, the ratio of thermal conductivity to the electrical conductivity is proportional to the absolute temperature, and this is known as Weidmann-French law. And near absolute zero temperature, the resistivity of some metal drops to zero. Hence, they show superconductivity. So we are going to study another chapter of superconductivity, because some material, when you cool it below certain temperature, okay, so they have got some resistivity. When the temperature is below certain temperature, the resistivity completely disappears. Okay, so this phenomena is called superconductivity. So in this semester we have a chapter called superconductivity. We are going to study that one later on. The resistance of metal increases with temperature according to this formula. That means RT equal to R0 into we can take common 1 plus alpha T. Alpha is called the temperature coefficient of resistance, okay, and T is the temperature. And R0 is the resistance at 0 degree Celsius. So these are the assumptions of the free electron theory. So actually, if I briefly state this one, that means in a metal, if suppose you have a certain piece of metal, so according to the free electron theory of the metal, electrons are free throughout the whole piece of the material. So that is the free electron theory. And free electron theory successfully explains some of the property of the material. However, there are some properties like distinction between metal, insulator, and semiconductor cannot be described using this free electron theory, and also some other things. So that is why the classical free electron theory was a little bit improved, and which is called quantum free electron theory. And according to the quantum free electron theory, you see, it says electrons are free. Like this is the positive ion core, this is the positive ion core, positive ion core, positive ion core in a solid. You know that they are arranged in some regular and periodic manner. So classical free electron theory is slightly modified in quantum free electron theory. You see, in a classical free electron theory, electrons are, if this is the whole piece of the material, electrons are free in the whole piece of the material. But according to the quantum free electron theory of metal, electrons are free only surrounding its ion core over here. over here, and then there is a barrier, and then again the electrons of these ion cores are free here. Electron of these ion core are free here. The electron of these ion core is free here. Okay, and then look at here. So this is the electric potential as a function of the distance, and this was actually, to treat this one mathematically is difficult. Kronig and Penney, actually, Kronig and Penney, two scientists, they said that just there is a model, and according to the Kronig Penney model, so they just use, this is called square wave potential. Instead of this curved nature, they said, okay, so electrons are free in this region, and then there is a barrier, and then electrons are free over here. So, so that is how. If we treat electric potential like that, so in that case, the mathematical analysis will become easier. Okay, and I hope you have studied Schrodinger equation in your college level chemistry book. Okay, Schrodinger equation is this is actually only one-dimensional Schrodinger equation. Okay, d square psi dx square twice m by h car square e minus b psi equal to 0. And when, so you have a two region here where there is a potential, and other has an so electric potential is over here. So in some region electric potential is there, and in another region electric potential is not there. So you see the electric potential. So this is the periodic arrangement of atoms in a solid. So ion core is there, and electron is there. According to the classical field electron theory, electron is free from anywhere. According to the classical field electron theory, electrons can move anywhere in the piece of the material. However, in case of quantum field electron theory, it is free surrounding the ion core, Okay. Now potential here, and this is called the periodic distance. Or later on we are going to study this thing. This is called the lattice constant as well. So B at x and B at x plus a will be the same potential, because it's a periodic nature. Okay. So A is called the periodicity of the lattice, or periodicity of the atom. So we will study Kronig Penney model to describe the origin of the energy bands. So this is the mathematical treatment, and this is the quantum mechanical treatment. I think you will find it a little bit difficult because you haven't studied wave theory of the electrons or the quantum mechanics. Okay, we'll use the simple quantum mechanics. We're going to use only the one-dimensional Schrodinger equation here. Okay, so one-dimensional Schrodinger equation, as I said, Schrodinger equation is this is the Schrodinger equation when the potential is there. When the potential term is 0, okay, then Schrodinger equation will become this one. So as I said, in a materials, when x lies between 0 and a over here, when this is the origin 0, when x is 0 to a over here, I said the electrons are free. So this is in region 1. Electrons are free. Electrons are free means their potential energy is 0, and then there is a barrier. There is a barrier means it is a bound system. Okay. So and the barrier height is V0. That is the electric potential. So in region 2 there is a barrier, or this is also region 2, and then again there is a region 1, and then again region 2. So we will have, please note carefully, we will have two different Schrodinger equation here. One is Schrodinger equation for region 1, and Schrodinger equation for region 1 will be this one, d square psi dx square twice m by h square e psi equals 0. I think you know this one. This is a differential equation for actually simple harmonic motion. So exactly the same thing. Exactly, you see in region 1, electrons actually move periodically over here. So they will move here according to the following the simple harmonic motion. And in region 2, electric potential is not zero. So region 2 means when x lies between this one, 0 and -3, or over here, from here to there. This is region 2, this is also region 2. So for region 2, our Schrodinger equation will be this one. Now we can simplify this equation 5 and equation 6, choosing twice me by h square as alpha square, and twice me minus b naught by h square as beta square. If we choose this one, so equation number 5 will become d square psi by dx square alpha square psi equal to 0. That is in region 1, where the electrons are free. And this equation number 6 will become this one, where it is not free. That is it is a bound system, or where there is a barrier potential is there. Now these are the differential equations. In your mathematics class, you have learned how to solve a differential equation. For solving a differential equation, we choose a trial solution. So as the electrons are moving in a simple harmonic motion, as I said earlier, so the simple solution will be a plane wave, which is e to the power ikx. So e to the power ikx is basically cos kx plus I sin kx. You know this one from, it's called Euler equation. Cos kx plus I sin kx. Okay. So the solution will be the appropriate for both region, will be the form of a plane wave with the ikx modulated with a periodic function ukx. So we choose a trial solution psi x. Oh, psi is called the wave function of the electron. Okay. So solution is psi x equal to the power ikx and then ukx. So at first, here there is a double derivative. So at first you will differentiate this one first. At first you will find d psi dx. Okay, and then you will differentiate again. So you will have d square psi dx square. So d psi dx will be this thing. D square psi dx square will be this thing. Now we will substitute the value of d square psi dx square in equation number 8 and 9. So if you substitute this value in equation 8, we will get this equation. And then if you substitute this value in equation number 9, then we will get this value. Okay. So if you substitute this square dx square in equation number 8, you will get this one. And then from here you can write, to make it simple, we can write this square u here, e to the power ikx common. So e to the power ikx is not 0, so its coefficient will be 0. So this square psi dx and this value will be 0 when the electrons are free. That means when x lies between 0 and a, That is mean in region 1, which we call region 1 in figure 1. In this figure, region 1 in this figure. Okay, so you see, we are trying to solve a differential equation, these equations. Okay, and after using this trial solution, we end up in another differential equation. Okay, so now again you have to solve this one. To solve this one, you will choose. So actually previously it was the differential equation of psi. Now we have a differential equation of u. So in this case, we will choose u equal to the power mx. Okay, so in that case, again you will differentiate this one, du dx will be this one, and d square u dx square will be this one, and substitute the value of du dx and d square u dx square in equation number, what is the number? Equation number 11 and equation number 12. And if you substitute it in equation number 11, you will have this thing. And then to simplify this thing, we can find out the value of m. Okay, so value of m. So here is a plus minus sign. So m will have two values. One is m1, another is m. So hence the general equation will be a e to the power, this one mx. Our solution is e to the power mx. So it will be a e to the power m1x plus b e to the power m2x. So that is for region, is becoming complicated. That is for region 1. And then for, if we substitute this one in equation number 12, we will get this one. So first solution U1 is this, and in case of when x in for region 2, we'll have this equation. Now here where U1 and U2 represents UKX in region 1 and region 2 respectively. Here we have used some constant. You can see it's A, B. In for this one we have chosen A, B, and for this one we have chosen C and D. Okay, so A, B, C, and D are constant, and this constant may be obtained by applying the following boundary condition. What is the boundary condition? So boundary condition is for region 1 and region 2 at x equal to 0. If you go back to the figure, so the value at x equal to 0 and x equal to a, the value will be the same. Okay, that is what I said. So value of this one, u1x at x equal to 0 and u2x at x equal to 0, their value should be continuous, it will be same. And also their first derivative will be also the same. And the value of x equal to a and x equal to minus b is also same. So let me show you the figure. At equal to a and minus b also the same. Okay, so this is the boundary. So at x equal to 0, this value and this value should be the same. Okay, again this value and this value should be the same, and their first derivative should be the same. So these are the conditions. We call these are boundary conditions. And applying these 4 boundary conditions, we will get 4 different equations from 13 and 14. Okay, so for first condition, we'll give you a plus b equals c plus d. Like this one. U1, if you substitute x equal to 0, so it will be just a, x equal to 0, it will be just b. And from this equation, it will be c and b. So it will be a plus b equal to c plus b. So it's just algebra. And then in the first derivative, if you put, you will get this equation, and and from the third condition you will get this equation, from the fourth condition you will get this equation. So we end up at 4 different equations, and we have 4 different equations and 4 unknown ABCD. If we solve it simultaneously, then we can find out the value. The constant A, B, C, and D can be determined by solving equation 17, 18, 19, and 20. And thus, the wave function U1 and U2 can be obtained. So these 4 equations, 17 to 20, have solution only if their determinant of the coefficient of A, B, C, and D vanishes. Okay. So if you apply this condition that the determinant is vanishes, then we will arrive at these equations. Okay. And now if you plot, this equation is actually quite complicated. To express it more simplified form, Kronig and Penney suggested a delta function. So delta function is such as when B tends to V0, the barrier, you see there is a barrier height. When there is a barrier height V0 in Kronig Penney model, and they chosen when V0 is very high, V0 tends to infinity. So this is actually V0, and that's the width of the potential. When V0 is very high, this B will become very small. So that means V0 tends to infinity when B tends to 0. Okay, so in that case, V0 B will be, so you can choose V0 as infinity and B as 0. However, V0 B is actually finite. Okay, so in that case, sine hyperbolic beta B will be beta B, and cos hyperbolic beta B will be 1 as B tends to 0. So this, if we apply this condition, V0 tends to infinity, then equation number 21 will become this one. So this becomes simple. Now in this case, m V0 B by h square as we chose this one as P. If we choose this one as P, then it will be P sine alpha A by alpha A plus cos alpha A must be cos Ka. So this equation 23 represents a condition for the wave function, and P is referred as, P contains this one. P is referred as the scattering power of the potential barrier, and it represents the strength with which the electron in a crystals are attracted to the ion. The term, this is actually V0B. Term V0B is called the barrier strength. With an increase of P, an electron is bound. When P is high, that means electrons are bound more strongly to a potential well, and when P tends to 0, the electrons are free. So the right hand side of the equation 23 can take the values between this is the cos K alpha. So the value of the cos K alpha, maximum value can be +1 and my minimum value can be -1. Okay, but the left hand side exceeds this value. You see, this can exceed this value. So by plotting this left hand side of the equation 23 for a finite value of P, let's say for 3/2 against alpha A, if you plot this one, this dotted line will be this one. So now you can see that, and then if we draw a line at +1 and -1, only the values lies between +1, -1, +1 and -1 is allowed, and the value is higher than that of the +1 and lower than that of the -1 will be forbidden. Okay, so actually this gives you the allowed values. This is forbidden. So when lies between this one, this is allowed band, and then this one is forbidden, and then again allowed band, and then forbidden gap, allowed band and forbidden band. So this is the mathematical treatment of the. So the part of the curve which lies between +1 and -1 horizontal line are acceptable to the left hand side of the equation 23. From the graph, the following conclusions are drawn. Number one conclusion is the allowed values of alpha A. Actually, alpha A is the energy because we have chosen alpha A as twice m by h square. So this is the energy. Okay, so alpha in alpha energy is encapsulated there. So the allowed values of alpha A and hence the energy for which the wave mechanical solution exists are shown by the shadow in this one. I have already this one, and this one, or this one, this one. From the graph, we know that the conduction electron in periodic potential lattice ion possess the band of allowed energy, that is the shaded region, separated by the forbidden region, that means the unshaded one. So this actually explains the formation of the energy band in solid. And the conclusion number two is the value of alpha A increases, width of the, you can see the width of the allowed band actually increases. Width of the allowed energy band increases and width of the forbidden gap decreases. Okay. Now you see that the effect of bearing P. Now if you see this value was, this graph was chosen for a particular value of P, which is 3 pi by 2. And if we increase the value of P, okay, this is the effect of varying P. If P is large, then the curve crosses ±1 line very stiffly, okay, very stiffly, so that the allowed bands are narrower and forbidden bands are wider, okay, according to this figure. In the limit P tends to infinity, the allowed energy band reduced to a single energy level as shown in figure 8, this one. So this reduced to a single energy band. Okay, at P tends to 0. Hence, all energies are allowed to the electrons. Thus, by varying P from 0 to infinity, the energy of the electron will remain or will vary from continuous to the bound state. That is, free electrons to the bound state. Okay, so that's the number 3. And number 4 is, if we plot E as a function of K, EK Venn diagram, the free electron moving in a periodic potential of lattice can have energy value only in the allowed region or zones, and it is possible to plot the total energy of the free electron versus their wave number or propagation vector according to this one. So you see that allowed energy bands are +π by 2 to -π by 2. This is called the, so that means A is called the lattice vector and 1 by A is called the reciprocal lattice vector. So this one is called the first Brillouin zone. And then there is a forbidden gap, and then there is an again allowed band, so that is called the second Brillouin zone and third Brillouin zone, and so on. So it explains here. We observe that the curve is not continuous. It has a discontinuity at ±Ka and ±2 pi A by A and ±3 pi by A, and so on. So that means it is discontinuous at K equal to ±n pi by A. Okay. So when the K value lies between this one, it's called the first Brillouin zone. Okay. And when the K values lies between this one -π by A to 2 pi by A, or this is called the second Brillouin zone. Similarly, the higher order Brillouin zone can be found. Okay. So today we're gonna stop here.